Bismillahirrahmanirrahim. High voltage impulse generation. Okay, so first of all, we will study that what is impulse. Impulse is actually a very high voltage or the current for a very shorter duration of time. Okay, so for example, this is the time. Okay, in microseconds, this is the voltage or the current. Okay, so a very high voltage flowing through a circuit in a very short interval of time. So lightning is the best example of lightning is the best example for the impulse. So and for any insulator, okay, the insulator will be tested for HVAC, high voltage AC generation, for high voltage AC testing, high voltage DC testing, okay, and for the impulse as well, high voltage impulse. Okay, so for this purpose we need to have the high voltage AC generator, high voltage DC generator in the laboratory, and high voltage impulse generator in the laboratory, so that the insulator or the cable or any dielectric material which you want to test for these voltages can be find out. Okay, so for high voltage impulse testing, and before the testing purpose we have to design a high voltage impulse generator. Okay, so let's start. Okay, so first of all we have this waveform for the high voltage impulse. Okay, so T1 is the time required to complete 50% of the peak value for the this high voltage impulse. Okay, this is the high voltage impulse peak value, and the time required to come to reach to its 50% or zero point 0.5 vx vmax. Okay, this is the T1. Okay, so this is called the wave front. Okay, and now this is the wave tail. Okay, so the time required to uh, down, okay, comes down or the falling, the falling wave. Okay, so this is the rising, this is the falling wave. Okay, the decay. So during its decay, if it reaches to 50% of if its peak value, so this time will be actually D2. Okay, and we call it the wave tail. Okay, so the first kind are the example of the uh, impulse are the lightning over voltages, which are originated by the lightning strokes hitting the phase wires of the overhead lines or the bus bar of outer outdoor bus station substation. Okay, so some substations are indoor and some are outdoor. So there is no danger of indoor substations. Okay, but there is a high chance, okay, a high probability of striking the lightning, uh, the falling of lightning over the outdoor substation equipments. Okay, so the amplitude are very high, usually in the order of 1000 kV. Okay, 1000 kV. This is uh, the the value for the lightning voltage. Okay, and it may be more than this. Okay, as every stroke may inject lightning current up to about 100 100 kilo ampere. Okay, so and even more in the transmission line. So each stroke is then followed by the traveling waves, whose magnitude is often limited by the maximum insulation strength of the overhead transmission line. The rate of the voltage rise of each of such a traveling waves, okay, traveling waves is at its origin directly proportional to the steepness of the lightning current. Okay, this pattern is actually shows the steepness. Okay, how much steep is uh, this wave is. Okay, which may exceed 100 kV per microsecond. Okay, this is in microseconds. So 100, the flow of 100 kilo ampere in microsecond. This is a huge amount of current flowing through a circuit in microseconds. So this is a huge impulse, and the voltage level may be simply be calculated by the current multiplied by the effective surge impedance of the line. Okay, so too high voltage levels are immediately chopped by the breakdown of the insulation, and therefore traveling waves with steep wave front and even steeper wave tails may stress the insulation of the power transformers or other high voltage equipments severely. Okay, so for this purpose we will study the insulation coordination. Okay, there must be some insulation coordination between the insulation level and the protection equipments. Okay, so lightning protection system, surges, arresters, and the high and different kinds of losses will damp and distort their traveling waves, and therefore lightning over voltages with very different wave shapes are present within the transmission system. Okay, so the second kind is caused by the switching phenomena. Okay, so there are two main causes for the impulse voltage. The one is the lightning, which I have discussed. Okay, so the impulse, the causes, main causes for the impulse. Okay, so impulse, two main causes: lightning and the other is switching. Okay, switching phenomena. Okay, so the second kind is caused by the switching phenomena. Their amplitudes are always related to the operating voltage, and the shape is influenced by the impedances of the system as well as by the switching condition. The rate of the voltage rise is usually slower, but it is well known that the wave shape can also be very dangerous to different insulation system, especially to atmospheric air insulation in transmission system with voltage level higher than 245 kV. Okay, so when the voltage is greater than 245 kV, so there is a high chance of switching over voltages, which appears in the form of impulse. Okay, so both type of four voltages are also effective in distribution system as well, where they are either produced by the usual sometimes current limiting switches, or where they have been transmitted from the high voltage distribution system. So here they may often cause a breakdown of the electronic equipments as they will reach amplitudes of several kilovolts, and it should be mentioned that the testing of certain apparatus with transient voltage or the current is a need of today. So such test will involve electromagnetic compatibility test, which will not be discussed here. Okay. So the wave front and the wave tails. Okay. So usually the TP is equal to 250 microsecond. Okay, plus minus 20% is the tolerance value, and T2 is equal to 2500 microsecond. Okay, so this one is 250 microsecond, and this so sorry, this TP means the time required to reach the peak value. Okay, and this value is T2 value. This two is 2500 microsecond. Okay, these are the practical values. Okay, so the tolerance value for this is plus minus 60%, and the peak value is 250. This is not 250, this is the peak value is 250. Okay, so 250 microsecond, and the tolerance value is plus minus 20%. Okay, therefore we write it as 250 oblique 2500 impulse. Okay, so these peak values varies between 100 and 1000 microsecond. Okay, it depend upon the strength of the insulation system, and may be sensitive up to upon the voltage wave shape. So let's discuss the voltage generator circuit. Okay, this is the equation for impulse wave. Okay, V is equal to V naught exponential alpha t minus exponential beta t. Alpha and beta are the constants. Okay, we will study it in the upcoming slides. We can write it as in this form, in this format: e raised to the power alpha t minus e raised to the power beta t. Okay, where v naught is equal to v maximum in the peak value. Okay, similar to the Walton Cockcroft multiplier circuit, we have studied a single stage generator for the high voltage DC, which was voltage doubler circuit. And now, similarly, we will study the single stage impulse generator. Okay, and then we will move to the multiplier circuit for impulse generator. Okay, so the schematic arrangement of the single phase generator is shown in the next slide, in which C1 is a charge up to V naught U of t by high voltage DC source. Okay, and C2 is the load capacitor. So C1 will act as a the charge capacitor acts as a source. Okay, and C2 will act as a load capacitor, and we will take the output across this C2. Okay, R1 is the damping resistor. Okay, which represent this wave front. Okay, and R2 will represent this the steepness of this waveform. Okay, and this is called as R2 is called as the discharge resistor. Okay, and this is the voltage generator circuit, the single phase voltage generator circuit for the impulse. Okay, and the output of this C2 will be the equation of the impulse. Okay, so let's design this uh, the output for this the let's design the impulse generator circuit of single phase. So apply KVL. We have two loops, loop number one, loop number two. Okay, so in loop number one, V naught across the C1. Okay, Voltage acquired across the charged capacitor C1 is equal to I T R1 plus I1 minus I2, because our current is flowing in downward direction, current 2 is flowing in upward direction. Okay, so I1 minus I2 into R2 plus 1 over C1 IT. Okay, so this is the capacitance. Okay, the voltage dropped across the capacitor C1. Okay, so apply the Laplace transformation so that the calculation makes easy. As we know that for the source we have V naught over S, and I1, small I1 becomes greater. Okay, capital I1 R1 plus, okay, this T can be represented as S. Okay, okay, so I1 minus I2 into R2 plus 1 for the capacitor. Okay, as we know that the Laplace of uh, the the integration is 1 over S, whereas the Laplace of the derivative is simple S. Okay, so here is integration, so 1 over C1 and 1 over S I1. Okay, and this is the final equation, equation number 1 for the loop number 1, taking I1 common and I2 common. Okay, so now for loop number 2. Okay, so now for the loop 2. Okay, so we will move to the next slide. This is the equation for the loop 2. I2 minus I1 into R2 plus 1 over C2 integration I2 dt is equal to 0. Taking Laplace of the above equation, so I2 minus I1 into R2 plus 1 over C2 as I2 is equal to 0. Taking I1 I2 common, so we will get R2 plus 1 over C2s into I2, and I1 will be here so that the sequence may not disturb, minus R2 I1. This is equation number 2. So we will combine these two equations to form a matrix, 2 cross 2 matrix. This is the coefficient of I1, this is the coefficient of I2 for equation number 1, and minus R2 is the coefficient of the I1, and this is the coefficient of the I2 for the equation number 2. Okay, so voltage source for the I1, because the capacitors were charged, so was charged to V naught, so there will be some voltage appear across the capacitor C1, which is represented by V naught over S, and there is no voltage source in the second two. You can see that there is no voltage source because this capacitor C2 is not charged earlier, so it will act as a load only, so there will be no source. So here V is equal to 0. Now we have to find V2, means voltage drop across the capacitor. Okay, which is equal to 1 over C2 integration I2 dt, and the Laplace form of this is V2s is equal to I2 over C2s. So now we will get the help of the Kramer rule, and then we will find delta 2 or delta. So all of these we will done in the next portion of this lecture. Okay, so that was up till the equations and Laplace transformation and the introduction of the impulse generator and the causes for the impulse. Okay, so thank you.